right, today we're going to be talking about clause 11.5. Clause 11.5 in the standard is the clause that basically tells you what equipment you're allowed to use and what equipment you're not allowed to use in a safety application. And with a focus today on the logic solver, the PLC. So what PLC are you allowed to use? Under what circumstances? And what type of additional considerations, precautions do I need to take when I'm applying those PLCs, those logic solvers? And the answer is you're allowed to use any PLC you want. But there's a lot of requirements that need to be implemented. And just saying you could use any PLC you want is definitely underselling the problem, because if you need to do all these activities yourself, the amount of work, the amount of testing, the amount of engineering is going to turn your $100 PLC into a $500,000 project after you consider labor costs and all the additional engineering that you need to do. So I will explain what that additional engineering is. So what we're really kind of talking about is I'm gonna put PLCs into three categories with respect to safety instrumented systems, with those categories being a commercial off-the-shelf PLC. So this is a PLC that's making no claims related to safety. It just has inputs, it has outputs, it does logic. You could go to Automation Direct and you could buy one for $79, or, well, it was $79 last time I checked. There's been inflation. Or on the other end of the spectrum, there are safety PLCs. Safety PLCs are generally certified to SIL 3, and the benefit of the safety PLC is that they've done all the thinking and all the engineering for you, and you basically just install it and plug everything in, and you're off to the races, because they've done all the safety configuration work for you. In the middle is something that's certified, but it's only certified to SIL 2. So I'm going to tell everyone that if you have something that's certified to SIL 2, is it suitable for your safety application? Absolutely, it can be, but you need to follow all the requirements that are sitting in the safety manual. And a lot of times people don't know that there are requirements in the safety manual for all the stuff that you, the end user, need to do to make sure that it's safe. So sometimes that's a lot more work than you think it is. So I'll kind of go over what is all the work that needs to be done. And what I'm going to do this trying to stay away from any particular equipment vendor and kind of keep things generic. But those SIL 3 certified safety PLCs versus a commercial off-the-shelf PLC that you, the end user, have to safety configure, that's what we're going to be talking about today. All right. So let me get into the details here. I'm going to share my screen. And there are several things I have up on the screen, and I'm going to start in the standard, but then I'm also going to be showing you some of the slides out of the ISA EC50 class. Cannot recommend the ISA EC50 class enough. Myself, I teach it quite frequently. I know that AK is in the session. He teaches it frequently. Lots of good stuff. So I'll be referring to some of the slides here specifically. I will be focusing on this slide to kind of tell you how those SIL 3 safety PLCs do a lot of the work for you so that you don't have to do the safety configuration yourself. But I'm going to start and spend a lot of time actually in the standard itself talking about what safety configuration is. So let's go ahead and start here. As I mentioned, the focus of what we're talking about is going to be clause 11.5. And I've got my magic pencil here that I can write on the screen and stuff. So let me make this a little bit bigger so everyone can see it. Okay, so clause 11.5 talks about the requirement for the selection of devices, or specifically, what do I need to do to make sure that a component, a subsystem, a piece of equipment that apply in a safety application, how do I know whether it's okay for me to use that device? That's what's going to be contained in this clause, and it's a long clause, especially when we get into what the standard refers to as programmable electronic systems. Those of us that have been programming them for a long time will call them PLCs, programmable logic controllers. Basically, you all know what a PLC is. It's the computer that takes the inputs and converts them into outputs based on the logic. Okay, so in clause 11.5.1, the objectives are to tell you what are the requirements for a device to be allowed to be used as part of a safety application. And then to specify the requirements for a device to be integrated into an SIS, into the architecture of an SIS, and the acceptance criteria for devices that are used in a safety instrumented system. And the clause has requirements for field equipment and programmable electronic systems. This webinar is focusing on programmable electronic systems. Okay. In terms of general requirements, pretty brief. Let's hit it. This is the clause 11.5.2.1 has all the meat. Devices selected for use as part of an SIS with a specified SIL shall be in accordance with IEC 61508 or 11.5.3 through 11.5.6. So there are two ways that you can justify using a component in a safety application. The first one is that, over here, the manufacturer of that component designed, manufactured, tested that device in accordance with the IEC 61508 standard, which some of us lovingly refer to as the vendor standard. So when an equipment vendor makes the decision that they want to create a device that's specifically to be used for safety, they'll follow the 61508 standard in the design and manufacture of that component. So that the shorthand for that is going to be certified. Now, when I say certified, there's nothing in the standard that actually requires a device to be certified. Period. End of discussion. Full stop. You do not have to use anything in your safety instrumented system that is certified. But if you're going to put a device in the service saying that it was designed and manufactured in accordance with IEC 61508, how do you know? Well, to some degree, you have to trust the equipment vendor. I mean, you could go to their factory and check for yourself. But most of the time, when a vendor goes through the trouble of saying, yes, I built this component in accordance with 61508, they will have an independent third party like my former company that I co-founded, Exita, or TUV, and they will get that independent third party to provide them a certificate that says, yes, we checked this equipment vendor's processes, procedures, and they are indeed in conformance with IEC 61508. So that's why we use the shorthand of certified, because most devices that are built this way are certified. But I just want to be clear, certification is never required, ever, full stop, period, end of discussion. Not required. Okay, now there's this, well, if it's not certified, it needs to be in compliance with 11.5.3 through 11.5.6. This route is going to be called the prior use experience route, which means, okay, well, the device isn't certified, but I have used it. I've used it for a significant period of time. I am happy with the performance, and I have safety configured the device to be suitable for use in safety applications. So safety configuration is the primary topic of this discussion because it's actually quite difficult to do, and a lot of people don't give it the degree of consideration that they should be when they say, yeah, well, I have prior use experience with this PLC. Yes, but did you safety configure it? And there's no exemption to safety configuration. So you can't just take and commercial off-the-shelf PLC, put it into safety application right out of the box and think you're going to be good. There's a lot of work that needs to be done, and that's going to be discussed in clauses 11.5 through 11.5.3 through 11.5.6. Okay, 11.5.2.2 basically says that, when you select a component, it needs to be suitable for the application that you're putting it into, the external ambient environment, and also the process service that you're installing it into. Okay, so if you're going to use a device based on prior use, which means it's not certified, the vendor has not gone through the process of complying with 61508. What are those requirements? And again, 11.5.3 is going to apply for both field devices and logic solver devices. Number one, you need to give me evidence that the device is suitable for use in an SIS. So you need to collect some information to justify that you're going to be using the device in a safety service. Okay, I need to collect the evidence. What evidence do I need to collect? 11.5.3.2 says there are 4 things you need to consider. Number 1, quality management. So, all right, before I get into these 4 items, Chris, does someone have a question?
Yes. For the prior in use, is there a specific requirement about I have used for enough time,
Yes.
like at least run for 15 years with records?
That's down here. I will get to it. It's the 4th bullet point. I'm on my way there. Okay. So the first of the 4 items that you need to consider is that quality management program. Why? Why is the quality program important? Well, if you have model XYZ installed in the field and it's been working, you're having success with it, you know how to use it, you understand it, you're happy with it, and you want to put another model XYZ in a safety application, what you need to be assured of is that the model XYZ that I buy today is the same one that I have out in the field. And that's what a quality management system does. It doesn't really make sure that the device is good. It just makes sure that the design is consistently performed by, strict adherence to procedures and inspections and so on. So in order to make sure that the XYZ I buy today is the same as the XYZ that I have in the field, I want to make sure that the manufacturer has a quality program. Just like Connexus has that ISO 9001 certificate on the wall that says we have a quality program, your equipment vendor should have the same thing, and you should ask them for it. Second item, adequate identification and specification of the devices. So basically, just because I have success with a guided wave level measurement does not mean I will have success with a tuning fork level switch measurement. So we need for our experience to be with a specific type of device. I don't want to go and say that, the specific model number you need to focus in on. That might be too tight of a specification, but absolutely we need to be concerned about manufacturer. We need to be concerned about the mechanism or the type of device that's actually being used. Number three, we want experience in the same operating profile, because a device that's used in a tropical location to measure natural gas might have a different performance than that same exact device being used in an Arctic environment to measure hydrofluoric acid. Okay, so similar operating environment, both ambient and service description. And finally, you need a certain volume of operating experience. So I need to have used that device for a certain amount of time before I'm able to say, yes, I have adequate prior use experience. What is the volume? How much? Is it 1 year? Is it 10 years? Is it 1,000 years? How much experience do I need? Well, some people that are really focused on certification, that yeah, the term I'll use, some people that are talking their book, if they're invested in certification, will overcomplicate this. In reality, if your SIL verification calculations say that I have a mean time to fail dangerous of 30 years, well, your operating experience needs to justify the numbers that you're using in your SIL verification calculations. So if you claim a mean time fail dangerous of 30 years, you should have 30 years of operating experience. Now, it's 30 years of experience in equipment years, not calendar years. What's the difference? I don't need 30 calendar years of experience. So we're in 2025. So that means, do I need to go back to 1995 to have 30 years of experience? No, it's equipment years. So 30 years of experience can be one device for 30 years, or 3 devices for 10 years, or 10 devices for 3 years, and so on. So 30 equipment years of experience is a good rule of thumb. Okay, so all those items are telling me what I need to just simply say this device is acceptable. And then, another clause here, 11533, basically talks about some of the documentation, making sure that management of change is applied so that we don't change the device and obviate everything else. Okay, now we're going to move on to 1154, and in 1154 is the beginning of our talking about programmable devices. So programmable devices add an entirely new level of complexity because you can change their design, you can change their configuration for your specific application. Now, 1154, I'm not going to spend a lot of time on because, again, we're talking about PLCs, and this clause is related to FPL. So FPL is going to be fixed program language. As you all should recall, there are 3 different types of programming that are used in safety applications. There's going to be FPL, there's going to be LVL, and there is FVL. So FPL is what clause 1154 talks about, and that is fixed program language, which means that the device contains a program, but it's fixed. You cannot change the program. The equipment vendor put the program into that device. You can't change it. You can't modify it. You can't manipulate it in any way. Think about a smart transmitter, a smart pressure transmitter. A smart pressure transmitter is running a program. It's got silicon, it's running a program, but that program is fixed in memory. You can't change it. The only thing that you could do is change the parameters like the 0, the span, and so on. But you can't change the program itself. So since we're talking about PLCs, I mean, this is important for field devices, but it's not a PLC issue. So let's go ahead and move on to the requirements for LVL. So what is LVL? LVL is limited variability languages. And for limited variability languages, that means that you can manipulate the program to make the device do different things, but you're limited in what you can actually do in the program, which is different from FVL. And FVL is a full variability language. So for a full variability language, you need to be thinking about things like C, C Sharp, Java, JavaScript, Pascal, Visual Basic. Those languages allow you, to take full control of the machine. And when you could take full control of the machine, you can do all kinds of bad things, like you can lose pointers to where your memory is located. You can create memory leaks. You can put your device into an infinite loop that when it enters it, it will never come out. Those are all dangerous failures, and they're easy to make in a full variability language, which is why when you're using a full variability language, you need to go into the 61508 standard and follow the hundreds of pages of rules for software development in 61508. Whereas if you stick with LVL, you can follow the 3 to 5 pages of rules in this 61511 standard. So LVL limits what you can do, and that's going to include things like function block diagrams, ladder logic, sequential function charts, those things that are provided to you by the equipment vendor. So the clause 1155 is going to be when you're using limited variability languages. And now we're going to delve into this a little bit deeper, but I see that there is a question on the board.
There is. Companies usually have an approved vendor list that is based on the confidence that the installations are in similar operating environment and have statistically significant volume of operating experience. Does that mean I don't need SIL certification on these devices if I choose the prior use route?
That is correct. That is absolutely correct. And for a sensor subsystem, or basically anything that's not programmable, valves, solenoids, transmitters, switches that are either not programmable or have a fixed program language, you're pretty much good to go. Now, you can also use that prior use route for PLCs, but what we're going to see here very shortly is that a PLC will need to be safety configured, which is going to add a lot of complexity into it. Okay. And yeah, that's what we're getting into right now. So if you're using an LVL programmable device based on prior use, you are allowed to use it in a safety applications, but right out of the gate, that commercial off-the-shelf PLC, you can only use it in SIL 1 or SIL 2 SIFs. So if you have a SIL 3 application, or God forbid you have a SIL 4 application, prior use is not an option. Period. End of discussion. For SIL 3 and SIL 4, you have to use a safety PLC that was designed and manufactured by the manufacturing organization in accordance with 61508. So safety PLCs absolutely required for SIL 3 and SIL 4. The only time you can use commercial off-the-shelf PLCs is in SIL 1 and SIL 2. Okay, so that's the first restriction. Second restriction, requirements of 11.5.4 apply. Again, this is that fixed program language. So everything that applied for fixed program language, you're going to apply here. 11.5.5.3 talks about differences between the operating experience and so on. Talks a little bit about systematic faults. I'm not going to belabor that. Uh, and then 1154, just a little bit more motherhood and apple pie. When you're looking at your operating experience, you're going to want to consider, whether your experience is in the same SIL range, it's in the same complexity and functionality of the devices. Okay, so far, 11551 actually has a lot of meat to it. 11552 through 4 are just kind of a little bit of motherhood and apple pie about thinking about whether or not you actually have sufficient operating experience. 11555, this is where the rubber meets the road. This is where all the complexity hits. And this is where, if you don't understand what this clause means, you have just walked yourself into a whole lot of trouble. So, if you're using a PLC in a SIL or a commercial off-the-shelf PLC in a SIL 1 or SIL 2 application, you need to safety configure that device. What does it mean to safety configure a device? Well, safety configuration of the device means that these 4 bullet points need to be true, and you, the end user, need to make them true. You cannot rely on the equipment vendor to make them true. Now, if you bought yourself that SIL 3 safety PLC, the equipment vendor is going to do all of this work for you, and I'll show you how they do it. And, when you pull that PLC out of the box, all this stuff has been done. But if you're using prior use experience for a commercial off-the-shelf PLC, maybe something you bought from Automation Direct for 79 bucks, you have to do all of this stuff yourself. So what are the things that you need to do for safety configuration? You need to understand the safe failure modes or unsafe failure modes. So you, the end user, basically need to do a failure modes and effects and diagnostics analysis. You're going to need to do an FMEDA. You're going to need to list out what are all the ways that this device can fail. And for each failure, you need to determine what the mode is. So is that going to cause a safe failure or a dangerous failure? Is it going to cause my outputs to be frozen energized? And am I in a de-energized to trip application where that would be dangerous? Then you need to look at diagnostics. So when that failure happens, how can I diagnose that failure has happened and do something about it? So this one bullet point is a massive amount of work to think through, to document, and to actually build out, program, and supply all the extra equipment. I am going to walk you through this as part of this webinar and show you the common failure modes and what you need to do about them. Okay, so a lot more on that coming up, but I'm going to walk through the standard first. Okay, so number one, I need to know what all the failure modes are, and I need to make a determination about whether they're safe or dangerous. Then, for those failures that are dangerous, I need to use techniques of safety configuration to address those identified failure modes. So one of the failure modes, just let me give you an example. One of the failure modes of a commercial off-the-shelf PLC is that it locks up. So the program starts and for some reason the program won't finish. Maybe there's an infinite loop. Somewhat older Microsoft Windows users will recognize something called the blue screen of death. So basically, something went wrong with the computer. It locked up, it hung up, and now I got the blue screen of death telling me that I need to restart the computer. Okay, so if that happens to your PLC, it can happen. What are you going to do about it? Well, the answer is I'm going to implement a watchdog timer to de-energize my power to the field. So that is the a watchdog timer is a safety configuration that will address the identified failure mode. You need to go through that thought process and that engineering for every failure mode that's possible in your PLC. Again, we'll come back to this. I will hit the big ones for you and explain what these safety configuration techniques are. And generally, what I expect is when I show you how much work you have to do, you will just go buy a certified PLC instead of doing it yourself. But if you're going to do it yourself, more power to you. I'm a little bit of a, do-it-yourself weekend warrior myself. So, I understand the draw to that. I'll just explain to you what you need to do. Third bullet item is that the embedded software needs to have a good history of use in safety applications. What is the embedded software? It's the firmware that's running on the chips that are in the logic solver. So there's going to be firmware running in the CPUs, firmware running in comms modules, firmware running in I/O cards. You need to basically have a good experience with the software that's running in those pieces of equipment. And again, that's a matter of just having used the device and collecting experience over time. The fourth item is generally the easiest. You need to protect that device against unauthorized or unintended. Oh, that's going to be a little bit tricky. Protection against unauthorized or unintended modifications. Most people, their programming terminals for their PLCs are going to sit in a room, usually in the control room of your plant. Security includes, I need a key card to get through the gate to get into the plant. I need a key card to get into the control room building. I need a key card to get into the room that contains the computers. Once I'm in the room, I need to have a Windows password to actually log into the machine. And then after I log into the machine, I need another password to open up the engineering and maintenance software. So that is kind of standard security for unauthorized or unintended modifications, at least to the software. Making modifications to the hardware, well, a lot of that same stuff applies. And, people are generally not going to mess around with the hardware unless they know what they're doing. Okay, so all of this stuff needs to be done, even for SIL 1. And it's a lot of work, but it's possible. It's manageable. The stuff that you need to do for SIL 2, we at Connexus have only done it once because it is a very complex, very long-term process. But before I get into what's required to get to SIL 2, I believe we have a question that needs to be answered.
Yeah, isn't cybersecurity included in this clause 15554 as well?
Sure. I mean, there are other requirements related to cybersecurity that I would point you to that have a little bit more teeth. There's a clause in Section 8 that says you need to do a cybersecurity assessment to make sure that that you've considered all of the vulnerabilities of your system in cyber attack. And then clause 11.2 has a subclause that talks about engineering your system to ensure that you've achieved cybersecurity. Those clauses are going to be applicable whether it's a safety PLC or a safety configured PLC commercial off the shelf. So, which is why I didn't bring up cybersecurity, because it applies whether it's a safety PLC or not. That's going to always apply across the board. But yes, absolutely, cybersecurity needs to be considered. Okay,
Okay, hold
moving
on a second.
on. Oh, more. Yeah, sure.
Yeah, so for 11.555, does this mean it is better to buy a certified logic solver for SIL 1 and 2 instead?
I won't go as far as to say it's better, but what I will say is that the end user needs to balance all of the manual work and manual testing that they are going to need to do and how much that costs and what their competency to do that work is against buying that same stuff from the equipment vendor that does all that work for you. So there's kind of a cost benefit analysis that every end user needs to do to say, hey, do I want to do this safety configuration myself and buy a moderately lower priced PLC, or do I want to spend a little bit of extra money and have the equipment vendor do all this thinking and engineering for me? And in my experience, definitely for SIL 2, it's a lot less costly to just buy all the engineering and have it in the box from the equipment vendor as opposed to trying to roll it yourself. But every person, every company needs to make that judgment for themselves. Is that good for questions, Chris? I'll take
Yeah, I
that
think
as
we're good for now.
okay. All right. So moving on, there's everything that I just talked about is required for SIL 1. SIL 2 is an order of magnitude more work, more effort in what you need to do. So 11556 lays out these requirements. And basically, what it says is that you need to, if you're going to use commercial off the shelf and safety configure it, you need a formal assessment. So actually what the engineering that happens for a SIL 1 safety configuration, you don't need to have, you're not required to have formality in how you do it. But for SIL 2, you need formal documentation to show you what you've done and what the results were and how you implemented everything. I mean, that kind of documentation is not a bad idea even for SIL 1, but it's only required to be formally documented for a SIL 2 application. So that formal assessment needs to show that you're able to perform the required functions, prior use has been demonstrated, there's a low probability of failure of the device, either due to random hardware failures or systematic failures in the design, okay? That's kind of a motherhood and apple pie statement. The rubber meets the road at all these bullet points down here. So if you are going to safety configure your commercial off-the-shelf PLC to SIL 2, these are all of the extra things beyond SIL 1 that you must implement and document in your commercial off-the-shelf PLC. And I say you, I mean you. The equipment vendor isn't doing this for you, so you need to do it yourself. So item number 1, you need to do program sequence monitoring, which means that you need to make sure that all of your logic is firing in the correct order, and if it goes out of order, you will be able to detect that it's gone out of order and take appropriate actions. Okay, this is one of the weird things that I learned when Connexus leaned hard into programming. There are some programming language like JavaScript where you can't count on this line being executed before the next line. Sometimes a subsequent line will execute before the line before it is finished executing, especially if you have multi-threading. So in the multi-threading parallel computing world, you need to do a lot of work to make sure that your program is firing in the correct sequence. And if you want to use safety configured, you have to write that code. Protection of the code against modifications or failure detection by online monitoring. So you need to make sure that your code isn't being modified somehow by your own algorithm. So maybe you need to do a CRC, circular redundancy check, on your code on a regular basis to make sure that the code isn't changing either by malicious attack or accidentally. Whew, that'll be interesting. Failure assertion testing or diverse programming. So when you're testing your code, you're going to need to document that you inserted failures into your code to make sure that your code can detect that you inserted those failures. Diverse programming is a technique where you will use different people, different programming languages to run the same code. So back when I was at UOP, one of the first projects that I did in safety was our lock hopper control system. And in our lock hopper control system, it was a 1 out of 2 voting arrangement that I'll show you in the slides in just a minute here. And what it did was we had one Allen Bradley PLC 5 and one Modicon 984. And there's going to be diverse programming because you're using different software tools for the two different PLCs, but also we use different people. So one person programmed the PLC 5, another person programmed the Modicon 984. That's diverse programming. Sounds like a lot of work. It is, which is why UOP stopped using this kind of 1 out of 2 hodgepodge commercial off the shelf and moved to currently, I believe the lock hopper control systems are in Honeywell's Safety Manager, but don't quote me on that. I don't work for UOP anymore, so I don't know for sure. Okay, range check and plausibility checks. So you need to make sure that all your values are in their correct ranges and that the values that you're receiving from input cards and so on are plausible. So that's code that you need to write. You need to write your code in a modular approach using subroutines that are tested. You need to use appropriate coding standards, so rules for how your company writes code. You need to do testing of typical configurations and test cases that are representative of the operating profiles. So kind of an FAT on steroids for the commercial off-the-shelf systems. Trusted verified software modules. So when you're writing your code, you're gonna write subroutines. You're gonna extensively test those subroutines to where you test them before you use them. System needs to undergo dynamic analysis and testing. Back when I was at UOP and we were doing our testing, this is complicated. So if you think about an FAT, you're usually testing one input at a time and looking at what fires in the output. That's no good. Basically, what this clause is telling you is you need to be firing everything simultaneously. So at UOP, we developed test stands where we had a computer that was generating inputs and reading what the outputs are. And this computer, another PLC basically, was firing all of the inputs simultaneously and looking at all the outputs simultaneously. That's what we mean by dynamic analysis. Manipulate everything at the same time. Don't just do one thing at the same time or at a time, or you won't be able to detect a lot of potential failure modes. The system does not use AI and does not use dynamic reconfiguration. Whole other topic for discussion. AI, your neural networks, your machine learning are not deterministic. You can ask an AI something today and tomorrow, and it will give you different answers. We in the safety business don't like that. Now, IEC is writing a whole set of rules to allow you to use artificial intelligence in safety applications, but they are early in the draft phase. So right now, it's a no-no. And then documented fault insertion testing has been performed. So you need to basically insert failures into your system. These are going to be software failures. These are going to be hardware failures. So in your testing, you're going to need to basically break your PLC to see what happens. So you need to go into your I/O cards and snip the connection on the optical couplers to make sure that the diagnostics are able to detect that device failed. So you're going to need to sacrifice a lot of hardware in order to make sure that the system responds in the way that it's supposed to. Wow. Who does that? So when you're looking at all this stuff, you should be pretty concerned about even going to a SIL 2 application with a commercial off-the-shelf PLC. Okay, now, what I will tell you, and I'm going to take a little bit of a step back here, there are a lot of devices that have a SIL 2 rating. Now, most PLCs that have a SIL 2 rating, I wouldn't consider them safety PLCs. I consider them safety configured commercial off-the-shelf PLCs where the equipment vendor has done some of the safety configuration for you. They've done some of this testing for you, but you're still going to need to do a lot of the work. It's just that they have a manual that explains what work you need to do. So when you buy that SIL 2 certified PLC, the first thing you need to do is look at the safety manual to determine how much work the equipment vendor has dumped into your lap in terms of the engineering to make it actually SIL 2 rated. Okay, so I'm going to come back to that. Oh, so this is my discussion of the standard. Now what we're going to focus on is clause 11555 and these 4 bullet points, specifically bullet point number 1 and bullet point number 2. Understand the unsafe failure modes and apply safety configuration to address those failure modes. So that's going to be the next part of the discussion where I'm going to do a lot of drawing on the screen and I'm going to show you some of the slides for the from the ISA training class. So let me minimize the screen, but we are going to be coming back a little bit. So let me first show you, let me make this full screen. An example of a commercial off-the-shelf PLC and how you would use it in a safety application. What you're looking at here is an active parallel redundant system. So if you go back to that lock hopper control system that I was talking about from my UOP days, this top row is going to be channel number 1. That would be the PLC 5 channel. This row down here would be channel number 2. This was the Modicon 984 channel. And basically, when an input comes in from the field, it'll go to the PLC 5, and it will also go to the Modicon. Each PLC will do all of the work by itself. So it will convert the signal to a digital format. You'll do some logic in the CPU. You'll set an output, and that output goes to a voter. And the voter actually is generally just as simple as wiring two switches in series with each other for a de-energized trip system. So we have one switch that is PLC5, another switch that is Modicon, and when you wire them in series, either PLC is going to be able to de-energize your output. So this is kind of a very basic safety configuration of a commercial off-the-shelf PLC or two diverse commercial off-the-shelf PLCs. Now, what I'm going to talk about in just a second is the safety PLC. So how is the safety PLC different? Bear with me for a second. This is a little bit more fault tolerance, but I'm going to kind of focus on this slide here that talks about a more modern safety PLC. So in a more modern safety PLC, you do a lot of the same stuff. We're going to take our input, we're going to do an A to D conversion to digitize our input. We're going to do our logic in a CPU. We're going to do a D to A conversion in the output circuit. And then we're going to send that device out to the field. Now, the difference with a modern and most of the certified devices is what you see in the green. It's the diagnostic circuitry. It's the circuitry that will detect that a failure mode has occurred and then take the result of that failure or take the fact that that failure has been detected and bring you to a safe state. So if, for instance, one of the failure modes I'm going to talk about is that the input circuit doesn't switch off when the output goes de-energized. So the output goes de-energized, but the input circuit still thinks it's energized. Well, you could do comparison or impulse diagnostics to detect that that failure has occurred. And then in a modern system, the diagnostic circuitry will be able to open the circuit with its own dedicated separate switch. So what PLCs now are giving you is a ton more diagnostics and the ability to independently de-energize outputs, even though the traditional circuit, so the traditional circuit that I showed you on the other slide is still sitting up here on top, but we have a diagnostic circuit that is also going to be able to de-energize your output. So that additional diagnostics and ability to independently de-energize the output, that's what your modern safety PLCs are getting you. And when you're talking about diagnostic coverages that are in the 99% range, that gets you a lot of safety. And not only do we have diagnostics, most of these PLCs are going to give you redundancy. So what you're looking at here is commonly referred to as a 1 out of 2D system. Probably you want to, that D means diagnostics, and that your diagnostics can de-energize your outputs and bring you to a safe state. That D is more of a marketing term. It's not discussed or defined in the 61508 or 61511 standards at all. But it is something that is commonly used in the industry. Now, there are a lot of vendors that will use this 1 out of 2D system. There are vendors that will basically take two 1 out of 2Ds and make a quad system. So basically effectively a 2 out of 4, but it's more complicated than that. And even the modern safety certified SIL 3 systems that are triple modular redundant are also going to have this advanced diagnostic circuitry, but they're using a 2 out of 3 voting arrangement instead of 1 out of 2 or 2 out of 4. But the key, I'm not going to dwell on 2 out of 3, 2 out of 4. What I'm going to focus on is this circuit down at the bottom, the diagnostic circuit, what it's doing and how it's achieving a whole bunch of safety for you that the equipment vendor has built into the system. They've designed it, they've manufactured it, they've tested it, so you don't have to worry about it. But if you're using a commercial off-the-shelf PLC, guess what? You are responsible for designing and implementing everything that's green yourself. And unfortunately, a lot of times, it doesn't happen. The vendor didn't tell you that you needed to do it, or it might be in the safety manual, but nobody highlighted it before you bought the system that work needs to be done. So now let's get into a little bit about what this work is. What's going on in the diagnostic circuitry? What is actually happening? So I'm going to escape out of here, and I am going to just bring up a OneNote, and I'm going to have a few things that I'm going to talk about for safety configuration. For safety configuration, step number 1 is going to be that failure modes, effects, and diagnostics analysis. So what I'm going to work through here is I'm going to create a list of failure modes. So let me get rid of this, and I'll come back to this later and say, so what are the failure modes of a PLC system that I need to think about when I'm designing the system? So let me just make a quick list of the failure modes, or kind of high-level failure modes. But I will give you the caveat that every PLC is different. Every manufacturer is different. And I'm just giving you some high-level ideas. For your specific PLC, you're going to need to drill down in a lot more detail on these things. Okay, so for some failure modes, number 1, loss of power. If I lose power to my PLC, that's a way that it fails. And I'm going to talk about 2 different power supplies, one to the field and one to the PLC. So generally, when you're designing your safety system, you're going to have 2 sets of redundant power supplies. One is going to be powering the PLC itself, and then the other set is going to be sending power out to the field for the field devices. Now, loss of power is generally going to be safe. So remember, in your FMEDA, the first word is failure, the failure itself, and the second word is mode. So when that failure mode happens, what is the effect? Is it going to be safe, or is it going to be dangerous? Now, most of the time when we're designing a safety PLC, we are going to implement DTT, or de-energize to trip. What does that mean? So if I have a de-energized to trip system, that means when I lose power, the final element is going to go to the safe state. So if I have a shutoff valve, what I'm typically going to do is I'm going to use a valve that has a spring that will force it to go closed in the safe condition. And then when I want to run the plant, I'm going to pressurize the piston on the actuator to open the valve. And furthermore, I'm going to supply air to the actuator through a solenoid valve that I need to keep that solenoid powered in order to keep the valve open. So for de-energize to trip, I remove the power from the solenoid. It causes the air in the actuator to vent, and then the valve goes to the safe state. Now, the standard says that you can use either energized to trip or de-energized to trip. So if you're using de-energized to trip, loss of power is generally a safe failure, and we don't need to do anything special to deal with it. Okay, cool. So let me erase here to give myself a little bit more room to work. The second failure mode is, I'm going to call it input stuck. So, and this could be true for a analog input or a digital input. So, my switch in the field is energized under normal operating conditions, and then it's going to de-energize when I go to a safe state. Well, there are failure modes that you can de-energize the output, but or I'm sorry, de-energize in the field, your field circuit, but the safety PLC doesn't know that you failed. And it continues to apply power. So input stuck, this could be for an analog input or a digital input. 3, the output can be stuck. So there are mechanisms to energize or de-energize to the field. Some PLCs are going to use an electromechanical relay to do this switching. Most PLCs are just going to use a transistor. A transistor can get stuck in a mode where it's going to pass current. So when you tell it to close, there's a chance that it won't close. So output stuck. For every output is another failure mode that we're going to be concerned about. And it can be dangerous. Both input stuck and output stuck are going to be dangerous. Yes, questions?
Yes. When you identify dangerous failure in the FMEDA, do you need to explicit detect or undetect?
That's the safety configuration. You need to detect that this failure has happened, and you need to take action to manually move the system to a safe state. So for all these failure modes, I'm going to show you what the safety configuration technique is. Okay. My fourth item is going to be program freeze. So this is the Microsoft Windows blue screen of death. The program, for some reason, got hung up and it's no longer executing. When the program gets hung up and is no longer executing, the outputs are going to be stuck in whatever state they are for eternity, or at least until you reboot your computer. So that type of failure is also dangerous. And then the last one that I'm going to talk about is just, I'm going to say, logic failure. So modern PLCs have a lot of ways to self-diagnose that they've failed. So you can have things go wrong in your PLC, like a stack overflow. You tried to push more memory into a buffer than you have memory available, which is going to push memory out. Now what's in your buffers is no longer correct. That's a dangerous failure mode. How do you know that that's happened, and what do you do about it? And that's going to be a lot of programming. Okay, so these are the big 5 items that pretty much any PLC you use is going to need to address these failures. It's going to need to have techniques to address these failures. What I'm going to show you are the safety configuration techniques for a commercial off-the-shelf PLC. And then I will also show you the safety configure or how the equipment vendor does this work for you when you buy a SIL 3 safety PLC. And then I'll kind of end the day with the kind of halfway middle ground that you get when you buy something that's SIL 2 certified, where basically the equipment vendor writes you a manual to explain how to do the safety configuration yourself. All right, so I'm going to not remove this screen, but I'm going to minimize it a little bit. And I'm going to come back to the ISA training class here, and then kind of show you how some of this works. So item number 1 is going to be loss of power. So how do I detect that there is a loss of power, and what do I do about it? Well, for loss of power, your main technique that you're going to use for safety configuration is de-energize to trip. Okay? If you're using energize to trip, things get complicated. But if you use de-energize to trip, basically when you lose power, the outputs to the field are going to de-energize. That's going to cause all the field devices to go to their safe state. So loss of power failure mode, go with de-energize to trip. If you want to go with energize to trip, there are requirements in the clause that are going to basically say, well, I need to detect that I've lost power and put up an alarm that someone can respond to. So basically, even if you're using energize to trip, I'm going to power supply for the, I'm going to draw a couple things in here. Actually, let me remove this. So I'm going to have a power supply for the PLC, and I'm going to have a power supply for the field. And I'm going to put my positive and negative on these. And basically, with loss of power, you can measure the voltage and put in a voltage low alarm is the safety configuration that you're going to need. So basically, you're going to need alarms on your power supplies to tell you that the power supply to your PLC, to your safety PLC, or to the field has failed. And you should do that whether you're doing an energized to trip system or a de-energized to trip system. But for an energized to trip system, that alarm telling you that your safety PLC power is gone is a requirement instead of a nice to have, as if it were a de-energized to trip system. All right, Chris, I see we have another question.
Yep. Do we need to mitigate all these dangerous failures identified in FMEDA or only to an extent where the PFD average meets the required SIL rating?
You need to mitigate. Well, actually, let me pause on this for a second, because the way that the standard is written, it says you need to address them. So let me go back into the standard and look at this clause again. So, and all right, so now I've got way too much highlighting here. So let me erase everything on this clause and read it again myself. So for SIL 1 applications, a safety configured PE logic solver may be used provided that all of the provisions are met. You understand the safe failure modes. So I just gave you a list of the 5 big ones, but you need to do your own digging to see if there are any other that are specific to your equipment. So you need to understand the safe failure modes and that use techniques for safety configuration that address the identified failure modes. So I'm not seeing anything in here that says you only need to address them to the degree that will allow you to achieve your SIL target. Okay, but I'm still kind of thinking about this in my head. So let's let that settle for a second. And I'm going to go down to this note. A safety configured PE logic solver is a general purpose industrial grade PE logic solver, which is specifically configured by the OEM, a systems engineer, or the end user for use in safety applications. So that doesn't shed any more light on the question. I'm going to go ahead and say that if you address every known failure mode, you are certainly in compliance with the standard. If you do not address every known failure mode, you are in a very gray area. So if you say, well, I know that my inputs can freeze up, but I'm not going to do anything about it because I've achieved my SIL target. The first question I would ask you is, well, how do you know you achieve your SIL target? You're getting numbers. Where do those numbers come from? Are those numbers for general purpose PLC contingent upon you doing the safety configuration? Are you using some sort of diagnostics that are going to allow you to use that device in a safety application? If you have no diagnostics, then you're probably going to run afoul of, hang on, I'm backing up to clause 11.4.9 or 11.4.8 that says FVL and LVL programmable devices shall have diagnostic coverage not less than 60%. So if you're claiming you have diagnostic coverage on your commercial off-the-shelf PLC and that your coverage is greater than 60%, which if it's less than 60%, you can't use it because of this clause. Where did that 60% come from? What are the diagnostics? And how are you achieving those diagnostics? So I would argue that if you're not doing this safety configuration of all the known failure modes, you probably don't have a 60% diagnostic coverage and you shouldn't be using the device anyway in accordance with clause 11.4.8. But I'm going to hedge my bets and not completely say that you must implement everything in order to be compliant with the standard. There is a case to be made that says as long as you have diagnostic coverage sufficient to meet your SIL target, that's good enough. But you're in a gray area, and I would basically say, yeah, if you're not doing all this safety configuration, show me where your diagnostic coverage came from. Prove your diagnostic coverage that you claim that you're achieving. And don't point me to a generic database that says, well, generic PLCs get, 60% diagnostic coverage. I'm not swallowing that. I want to see this safety configuration done. I really don't think that there's a reasonable case for not doing all the safety configuration that I'm going to show you. Okay, let's continue on then. Let me put this back where it came from. So our first bit of safety configuration is that I want a voltage low alarm on these devices, on the power supplies. That's going to address my loss of power failure mode. And VAL, what am I doing? Come on, Ed, learn. What I'm showing you is one power supply. You're able to achieve safety with one power supply. Most people are using redundant power supplies, so you're going to want this voltage alarm on both of those power supplies. Okay, so item number one, loss of power. What is my safety configuration? I want to have an enunciated alarm if I lose my power on either one leg of a redundant, and I want to do it for my PLC, and I want to do it for my field power. Okay, so that's configuration number one, power supply failure alarms. Input or item number four, failure mode number four. So I talked about failure mode number one. Failure mode number four is the program freeze. So how do I detect that my program froze and get my process to a safe state? What is my diagnostic? So the D in FMEDA is what diagnostic am I going to use to detect that that failure mode has occurred? And the answer to that is going to be the watchdog timer. So I'm going to add a new page here, and I'm going to type in watchdog timer. And then I will explain to you how a watchdog timer works. So I have a PLC. My PLC has an input card. It has a CPU. And it has an output card. Okay, the PLC is going to run its program on on a regular basis. So it's going to cycle. And usually we're talking about like 100 milliseconds, maybe 500 milliseconds, depending on what type of PLC you use and how big the program is. That cycle time is going to change. Now, what we're trying to detect is that this CPU is stuck in place. How can I detect that the CPU is stuck in place and not cycling? Well, what I'm going to do is I'm going to take one of the outputs from the CPU, and I am going to go into the coil, if you will, of a TDR, or a time delay relay. Okay, so the time delay relay, it basically, what a time delay relay does is it's going to have a set of contacts, and it will keep the contacts closed for a certain period of time and then open them when the time expires. So I'm going to have a time delay relay, and let's say I'm going to set it for 1,000 milliseconds. So basically, if I don't get a change in status, a pulse of this time delay relay, and I haven't gotten the power pulse to the time delay relay in 1,000 milliseconds, then it's going to come in and it's going to open up the contact. Okay, great. So I've got my time delay relay that I'm going to open up the contact. Well, what am I going to do with that contact? Well, let me explain a little bit more about how power distribution works. So I'm going to have a power supply for the field. Okay, it's got a positive and it's got a negative. And what I'm going to do is I'm going to take the power going to the field, and on my terminal block, I'm going to jump that power to a bunch of terminals, and then I'm going to send power to individual devices. So this could be, this switch could be, PSL1. This could be PSL2 out in the field and so on. So we're going to distribute that. Then the power from the field is going to come back, go to the input card, and then the input card is going to sync all the powers together and go back to the negative terminal. So that's how the power is going to be distributed in a typical PLC. So what I'm going to do with my time delay relay is I'm going to take that positive and I'm going to put it through this contact before I distribute it. So what did I just do there? I set up the situation where if this output stops pulsing, this contact is going to open up. When that contact opens up, I just de-energized everything out to the field, including, maybe this one is going to be to SOV1, which is going to close my shutoff valve. Okay, so that's how we're going to address the program getting hung up. It's with the time delay relay. So what did you have to do? For safety configuration, I had to write code to pulse the output. I have to install time delay relay. I need to cut power if TDR times out. So I needed to do all this. The equipment vendor didn't do it for me. When I bought my Automation Direct PLC, this wasn't built in. This wasn't installed. All right, before I go to a safety PLC, Chris, what's the question?
How could you distinguish between output stuck and CPU failure in this case?
I'm gonna hold off on that question because I will discuss that in detail when I explain how to detect the output stuck. So the program can be firing and the output and output to the field might be frozen in place. And I will get back to that because basically what we're going to do is we're going to wire our output back to an input. But that's still to come. So I will answer that question when I talk about how we're going to detect a stuck output and bring ourselves to a safe state. Okay, so now how does the equipment vendor do this for you when you buy a safety PLC, when you buy a certified PLC? So I'm going to go over here to my certified PLC, and guess what? There's a diagnostic circuit. So for your safety PLC vendor, they're going to have the watch, try to write this a little bit better. They are going to have a watchdog timer sitting on the circuit board of their PLC. If that watchdog and not only are they going to have it, they're going to have redundancy. So they're going to have watchdog timer 1, watchdog timer 2, 1 out of 2 vote. When this watchdog timer detects a failure, they will communicate to the diagnostic circuitry to open that circuit. So basically to open the circuits to de-energize all the power out to the field. So you see the difference between safety configured and certified. When you buy that SIL 3 certified PLC from a reputable manufacturer, the diagnostic of detecting a stuck program is sitting on the circuit board of what you bought. You don't have to do any programming. You don't have to do any purchasing of equipment. You don't need to worry about trying to figure out how you're going to de-energize to the field. The equipment vendor installed all that and programmed all that, and it's sitting on the PLC you bought. You couldn't turn it off if you wanted to. Okay, now Where is the middle ground? The middle ground is going to sit in this SIL 2 certification. So when you get a PLC with a SIL 2 certification, read through the safety manual, because when you read through the safety manual, they might end up telling you or basically giving you instructions for how to build that watchdog timer system that I just presented to you. And they will give you very good instructions that's very specific to the hardware you bought, but don't be fooled. You have to do it. You can't just say, well, it's a nice to have. If the safety manual says do it, this SIL has not been achieved unless you do it. So you have to do it. So SIL 2 systems, read the safety manual. A lot of SIL 2 systems have the watchdog timer built in. You don't have to do it externally manually. But read the safety manual. And for commercial off the shelf that is not SIL rated in any way, shape, or form, you have to do it yourself. All right, so that's failure mode number 2. Well, technically it's number 4. I went from 1 to 4. Let's backtrack now and go to, that's not what I wanted. Let's go backtrack now and go to failure mode number 2, which is going to be our stuck input. So how do I detect a stuck input? And what do I do about it? Well, let me add a new page and draw this out for you. So I'm going to start again with my power supply going to the field. And I'm going to have a switch in the field. Let's just call this a, come on, Ed, PSL. And then I'm going to land, let's say this is channel 1 input, and then you also have channel 2 input and so on. Then you're going to have something like a common that is going to come back to the PLC. So this is how you typically wire this up. Well, what can happen is that this device, and there's going to be something in here called an optical coupler. I'm not even going to try to draw an optical coupler, but actually, let me make this a little bit bigger so I can kind of show you what's going on in the circuit board. So in the circuit board, there's going to be some sort of switch that is going to convert this to digital. Okay, what if there's a failure that causes this switch to just basically fail short circuit? Now I can draw this a little bit differently. So I can open my circuit in the field, but if on the I/O card that I have a short circuit, this is never going to, it's never going to say that my switch de-energized. So this is a known failure mode. Short circuit in that optical coupler that's doing your A to D conversion is a known failure mode. How do I safety configure myself to address this? Well, I'm glad you asked. All right, let me try. I'm giving myself a little bit more room. What you're going to need to do is you're going to need to take that signal, and there's the A card here. We're going to need another input card. So we're going to need to take this signal, split it, and jump it over into card number 2. And I'm going to do a COM. And I'm going to go back. So now I'm going to have a logical A, and then that's here. So this is kind of actually let me draw this in ISA with my software signal. So I'm going to have a software signal now that is going to go into a compare. And basically, I'm going to compare these two signals. If the signals don't match, I'll just say mismatch. If I get a mismatch now, okay, so this is an A input card, B input card. I'm going to have another output that is the mismatch. So this is my mismatch output. So this is basically, if I go back here, come on. What I'm doing is I'm trying to basically create this diagnostic switch that says I'm going to open a circuit when I diagnose that there's a failure. That's what I'm trying to mimic here in my safety configuration. And that's going to be this output. So this mismatch output is going to go to another relay. And let's just call this the MTR, or the master trip relay. So when I de-energize the mismatch output from my output card, I'm going to de-energize my master trip relay. And when I de-energize my master trip relay, I'm going to disconnect my field power from my devices, the same way that I did with the watchdog timer. I'm basically going to take that power supply going to the field, and I'm going to chop it. So if I could go here, and that was my time delay relay, but I'm also got my master trip relay that's coming in here, and it also is going to be able to cut all the power going out to the field. Okay, so there, what did I do? What in my safety configuration? I have to buy 2 separate cards for every input. Well, I mean, obviously, you can wire more inputs to a card than one, but I need to basically land every input at 2 different cards. I need to compare the values of those 2 cards. If those 2 values don't are mismatched, I need to de-energize the mismatch output to a separate relay that's going to allow me to de-energize all my power to the field. So this is what needs to be done for every input to address the potential of a stuck input. Okay, now how does this happen in a safety PLC? Well, in a safety PLC, if you've got a 1 out of 2 system, there's going to be comparison diagnostics. So basically, if you look, it's kind of hard to see that these 2 channels are talking to each other. So what you're able to do in a safety PLC system is that comparison of card number 1 and card number 2 are going to get communicated to the diagnostic circuit, which is going to allow it to open. Okay, all of this done for you. You don't need to think about it. It's built in. You bought it. Also, with a safety PLC, you can do active diagnostics as opposed to just comparison diagnostics. So there's probably going to be circuitry here and circuitry here that is going to turn the power off, make sure that the switch changed position, then turn the power on. So you're continuously cycling the power on and off to make sure that that circuit is working. And if you detect that the circuit is frozen in place, you de-energize your output. So SIL 3 safety PLC, this is all bought in. You don't have to do anything. It's already built in. It's there. But if you're buying a commercial off the shelf, you needed to buy a new I/O card for redundancy. You need to write code to detect a mismatch. You need to have an output that will de-energize when you detect a mismatch, and you need to have an external relay that's going to de-energize all of your power to the field if you detect that a failure has occurred. All right. Next item. And yeah, this is going long. I was expecting a full 2 hours because this is an extremely complicated topic. Next one is output is stuck. So I have my input cards, my CPU, my output cards. I can run my logic to tell me that I need to de-energize the output, but if the transistor is failed, it won't de-energize the output. So how do I deal with this? What diagnostic am I going to use to detect that it's stuck? And then what action am I going to take? All right, so let's do another page. And we're going to call this the output stuck diagnostic. Come on, Ed, learn to type. Diagnostic. And then let's do a little bit of drawing. So now I have an output. And for my output, my digital signal is going to tell a switch to either open or close. Okay, and actually, let me draw that a little bit differently. So my digital signal is kind of working like the coil on a relay. And then there's going to be a switch. And so again, my power supply for field devices, I've got my plus, and I'm going to go through this contact. I'm going to go out to my field device. Actually, let me draw this a little bit differently. So that's positive and negative. And then the negative, let me conserve some space, is then going to go back to this minus here. So that's kind of out of the box how you would typically do it. So now how are we going to detect that there was a failure? Well, in addition to sending my power out to my solenoid valve, guess what else I'm going to do? I'm going to bring it to an input card. So I'm going to take my output value, bring it to an input card. And then I've got my digital signal. I'm going to communicate that here. And then I'm going to do a compare, where I'm going to compare the measured, so this is the measured value going out to the field. And then there's also, what the logic can tell me what was the command. So if the command and the measured value don't match each other, I've got another mismatch. So I'm going to take that mismatch and I'm going to go back to this guy. So, and I'll redraw it again on the other page, but it will be that same contact. So now I'm going to go to my output, and this is my mismatch between the command and the output. That will open the contact out to the field. This is going to go to the coil of my MTR master trip relay, and then that's going to basically de-energize field power from going out to the devices. Okay, so that's what you need to do for every output. You need to wire it back into an input. You need to do a command versus measured mismatch. If you have a mismatch, you need to de-energize that master trip relay to stop sending power out to the field. All right, so that's my output stuck diagnostic in a commercial off-the-shelf PLC. For a safety PLC, we've got our diagnostic circuit. So basically, the diagnostic circuit will measure what is actually happening with the switch. If that diagnostic circuit detects that the switch doesn't open, it's going to open its own switch in order to de-energize out to the field. Once again, done at the circuit board level by the equipment vendor. You don't need to configure it. You don't need to think about it. It's all built in, ready to go, no problem. All right, so hopefully you're kind of getting the magnitude of what, when you buy a safety PLC, what is all the stuff that's going on inside it that makes it so much, well, not so much more effective or expensive, a little bit more expensive than a commercial off-the-shelf PLC. There's a lot of diagnostic software, there's a lot of diagnostic hardware that are detecting all of the known failure modes, and if they are detected, de-energizing your output so you go to a safe state. Okay, let me go back here and hit the last item on our list. The last item on our list is a logic failure. So these are things, and I'm not going to do a drawing for this, but basically, your PLC vendors are going to have internal subroutines that will detect things like stack overflows. So what you need to do as the end user is grab the user manual, read through all the error codes that can be generated by the PLC, and decide if this failure mode is present, what do I do? So for instance, if you have a stack overflow diagnostic in your PLC, then you need to write your own code that says if the stack overflow flag is set to true, I want to de-energize that output that is going to the master trip relay to de-energize all of the power going out to the field. So this last item is an exercise of going through all the error codes and writing a big logic gate that says if these error codes exist, de-energize all my power going out to the field. And that's how you do that. Okay, so that's basically the big picture, the long and short of it. And as you can see, for the top 4 items, you have to buy new hardware. You have to program the PLC. You have to wire up all of your inputs and outputs so that you could detect these failure modes and bring the process to a safe state. What you need to ask yourself is, do I want to do all this engineering myself, or do I just want to let the equipment vendor take care of it for me? And if you buy a SIL 3 certified safety PLC, I can pretty much guarantee you that the equipment vendor did all the thinking, all the engineering, and all the programming for you, and all these requirements are going to be met out of the box. If you buy your commercial off-the-shelf PLC, none of this stuff has been done, and you're going to be responsible for doing 100% of it by yourself. The middle ground is our good friend, the SIL 2. So for a SIL 2, here are the downsides. First thing you need to do is you need to look at the safety manual, and you're going to need to implement the safety manual. And a lot of times when you buy a SIL 2 certified PLC, the safety manual is going to tell you that you need to put in a watchdog timer. It's going to tell you you need to wire all of your inputs to multiple cards and compare the results. It's going to tell you that you need to wire your outputs back to inputs and do a comparison diagnostic to de-energize the outputs. So Some manufacturers were able to get a SIL 2 rating by simply creating a manual that explains in detail how you can do all this work for yourself on their specific piece of equipment. So I'll kind of end the discussion with the caveat that just because it's certified doesn't mean all of this safety configuration has been done. It really only means that now, in some cases, it is done for you, but in some cases, they just wrote a manual that explains what you need to do, and that was enough for some certification bodies to give them a certificate. All right, so that's what I've got for you right now. I'll turn the floor open to some questions if you want to start typing them right in, but just kind of summarizing, you are allowed to use commercial off-the-shelf non-certified PLCs in safety applications. You could do that in SIL 1 or SIL 2. You cannot ever do it in SIL 3. SIL 3 certified PLCs, programmable systems, always have to be 61508 compliant. SIL 2 requires a lot of stuff that nobody's going to do. I, in my career, have seen one commercial off-the-shelf PLC certified to SIL 2, or not certified, safety configured to SIL 2. Getting to SIL 1 requires a lot of work in terms of safety configuration. Know all the failure modes. At a minimum, loss of power, input stuck, output stuck, program freeze, logic failure. Those 5 failure modes, at a minimum, you need to address. You need to be able to detect them. You need to be able to get yourself to a safe state if they are detected. Commercial off the shelf, you need to do that yourself. You buy a SIL 3 certified safety PLC, the equipment vendor has done all of that work for you. So do yourself a little bit of a cost benefit analysis to determine whether or not you want to roll it yourself or you just want to buy all this stuff directly from your equipment vendor. All right, Chris, can you tell me, do we have any new questions?
We do.
All right.
61511 nor 61508-1 mention the term certified devices.
Correct.
Does 61508 part 2 or 3 use the term certified? If not, what is the correct terminology or the recommended by the code?
No, it does not ever say certified. There is no point in time ever where you need to have a certified device. All that it says is, and the language is a little bit more complex. Let me erase this here to make it a little bit more clear, is the in accordance with IEC 61508 Part 2 and Part 3. So basically, the PLC needs to be in accordance with 61508 Part 2 and Part 3. That's the language. This is the specific language that the standard is going to use. It never says certified. And of course, as I mentioned earlier on in the discussion, we, and I do it myself, use certified as a shorthand because if you design and manufacture something in accordance with IEC 61508, almost always you're going to get a third party to certify it for you, because why else would your customers trust you?
Okay, what's the difference between compliant and certified?
Okay, compliant means that the requirements have been met. So just giving you an example, sorry about that. Part 2 has a requirement for fault tolerance. If the PLC has fault tolerance, it is compliant. Now, for it to be certified, your third party has to check to make sure that the fault tolerance has been achieved, and then they certify it. They certify that the requirement has been met. So the requirement being met is compliance. Having a third party check and verify that it's been met is certification.
Okay, thank you. I don't see any other questions. Does anybody have anything?
That was a lot to digest. I got to admit, this is probably one of my more hardcore webinars that I've ever given, and really getting down into the nitty gritty of the wiring of the PLC. So if you were able to stick with me the whole time, excellent work.
There is one more question, Ed.
Yep.
Because the certification by a third party always adds cost to the project, is a self-compliant statement by the vendor good enough?
Yes, but you, the end user, are responsible for the what you install in the plant. So if you're saying that a device is compliant with 61508, it's your response. If a vendor gives you a letter and they lied to you, they're liable, but you're liable too. So getting a self-certification or a letter from the vendor saying that they met all the requirements, even that isn't required. They could just say, yeah, it's compliant with all the requirements. And if it's true, then you're good to go. But how do you know that it's true? And when a vendor self-certifies, you're basically allowing them to use their judgment as to whether what they did is compliant or not. And you might disagree with with them as to whether or not the measures that they took actually achieve compliance or not. So, at the end of the day, you, the end user, are responsible for the equipment that you put in your plant. If you trust a vendor to self-certify, there's nothing that's going to stop you from doing that. You just have to you just have to be able to sleep at night.
Okay, that's all I see at the moment.
All right. Well, that's all I got for today. Thank you for hanging with me on this decidedly complex topic. I appreciate your time and attention.
Thank you again, everyone.